Okay, welcome to my talk on conformance-based doping detection for cyber-physical systems. This talk is meant to accompany our paper for FORTE 2020, which was supposed to be held in Malaga, but due to the COVID-19 situation, we are now recording this talk and it will be broadcast on the FORTE website. My name is Mohammed Musavi from University of Leicester, and this is joint work with several colleagues, namely Raina Dimitrova and Maciej Gazda from University of Sheffield, and Holger Hermans and Sebastian Biewer from Saarland University. Much of the work and the credit goes to them, and of course the remaining mistakes on the slides are all mine. So before I start delving into the specific topic of this talk, I would like to give you a broad overview of our research on this topic, and then I will delve into the subject of doping detection and how we have been dealing with it in this context. So our research group at Leicester mostly looks at trust in autonomous systems, and in particular we would like to apply rigorous analysis inspired by formal methods to ensure safety and to establish trust in autonomous systems. And for that we collaborate with many different companies, some of which are mentioned here, and also we do a lot of public engagement through many different media and channels. To give you an idea about trust and how we contribute to it, first of all, I give a formal definition of trust. Trust is about users' belief that the system is helpful and safe, particularly in very challenging and uncertain situations. And in order to establish trust, there are many different factors that contribute to it. One of the main factors that contribute to trust is technical transparency, and that's also our focus in our research group. And technical transparency can be established by achieving explainability of the decisions that a system makes, and also in the same spirit, our colleagues at Saarland have a large project on perspicuous computing, which is about being able to explain the decisions of autonomous systems. The other aspects are safety and security, and the final aspect is user experience. And we have a lot of expertise that pertains to these aspects of technical transparency. And as I said, we engage with the public in discussing this issue of trust and also raising awareness about trust in autonomous systems. And here is a website that we maintain for public engagement activities. It's driverless.github.io. A couple of projects that we run in this context. One is about platooning and connected autonomous vehicles. So we perform conformance testing in order to establish safety of connected autonomous vehicles, and we apply genetic algorithm and search-based techniques to come up with challenging scenarios that can exercise the corner cases and the extreme cases of the behavior of connected vehicles. The goal of this is to expose any risk that these systems can pose before their users. And also another activity is to find optimal design parameters for those systems. So the goal of this project is to increase trust through safety and performance, and also provide guarantees regarding the basic awareness protocols that underlie connected and autonomous vehicles. The other project that relates to this particular topic is about particle emission tests. And the approach is to use real data to learn from vehicles' behavior and run search-based techniques to expose possibly undesired behavior by the vehicle, which may emit more particles than what is allowed by the standards. It serves two different purposes. On the one hand, we will reveal those cases of doping and cheating where a manufacturer might have planted an algorithm or a device in the car that would modify the particle emission test when it detects that it's on the test and otherwise emit more particles. So that's one purpose. The other purpose is to come up with environmental friendly profiles for driving those cars, in particular when they are driven in automatic and autonomous modes. And again, the goal of this second project is about achieving trust through transparency. Now let me delve more deeply into the specifics of doping detection and doping detection in cyber-physical systems. So what is doping? Doping is about intentional intervention in systems behavior such that you change the behavior, but the change is against users' interests. There are many examples of doping in our daily practice. One is the diesel emission scandal. You have heard about that in the news, that some car manufacturers tampered with catalyst injection systems such that when they detect that the car is under emission test, they inject more catalyst into the exhaust, and hence the particle emission is significantly reduced, while when the car is driving on road, the amount of catalyst is far less, and hence it will emit far more particles into the air, which is not healthy for us, and let them get away with these type of engines that are polluting the air. The other type of doping is customer locking behavior that is exercised by many consumer electronic and computer manufacturing companies. They build in certain chips or software into their devices so that when you use third-party accessories, they can detect that and hence not allow you to use them. A third type of doping is malware that downloads malicious software into your mobile phone, and for example, when you're asleep and your phone screen is locked, it will start an algorithm for cryptocurrency mining and use your battery in your mobile phone for their own purposes. So these are examples of doping in our daily practice, and what we are going to do in this research is to formalize this and come up with algorithms that can detect doping effectively and efficiently. So the main approach that we use in order to detect doping is to define doping through the changes in behavior. So whenever a small change in valid input leads to significant changes in observable behavior, that could potentially be an indication of doping in the system. So typically you assume that if the system is behaving normally, namely it's not resonating a certain signal, whenever you make small changes around a valid input, that will result in small changes in valid output as well. Of course, this has to be verified by the domain expert that the system is supposed to behave in that way. However, if that is the expectation and suddenly you change a certain valid input and you see a significant change in output, that might be an indication that around that input space there is some doping happening in the system. And if this is not what the domain experts and users expect, then we can use it as evidence for doping. So for example, if you deviate the behavior of the car, for example by accelerating and decelerating slightly beyond the limits of the test cycle, and you see significant changes in particle emission, then that's a sign that the car is under doping to optimize particle emission for test cycles. In the other example, if you, for example, change the time of your mobile phone such that it goes, for example, to closer to midnight, closer to time when you're asleep, and you see a significant change in network bandwidth usage or battery usage, that might be an indication that there is an app that is using your mobile phone around those times. So if you could modify the input and see unexpected significant changes in output, that could be used as an evidence for doping. To formalize this, we need to talk about hybrid systems trajectories and continuous signals. So we need to measure the proximity of different signals to each other, both in terms of value and in terms of time. So consider, for example, the gray signal over here, which is a valid input regarding the velocity of a car. So this is a trajectory that should be driven according to a test cycle. And assume that we deviate a little bit from it in this dashed red line by moving the signal a little bit upwards by the value epsilon, right? If the particle emission in milligrams is supposed to be like the gray signal over here, and suddenly you see a huge jump, much more than what a domain expert would expect, another epsilon value over here, though these two epsilons could be different values, right? Then you are likely to have found a case of doping. Likewise with timing, so if by adding a slight phase to your signal you see significant changes to the output, that also might be an indication that you have found doping. And the combination of these shifts in time and in value could give you a quantitative measure for doping that should be set by the domain expert for each example you're looking at. So we went about in the literature and tried to find notions of conformance that could characterize these changes in input and output and characterize this notion of proximity. And we found two examples in the literature. One is called tau epsilon conformance. It's originally due to Hossam Abbas and Georgios Finakis at Arizona State University. And it's a very simple notion. It basically says, assume that you have this a blue signal as your specification, your original test cycle, and you have this black signal as your deviated input or output. Then I say these two excuse me, I say these two trajectories are in tau epsilon proximity of each other whenever for each and every point on the blue line you can find a point on the black line that is at most epsilon apart in value and at most tau apart in time. In other words, for every point on this blue line you will be able to find a point on the black line, on the black trajectory, that falls in a rectangle that is 2 tau wide and 2 epsilon high, right? So that's the notion of tau epsilon conformance that was proposed a couple of years ago by Abbas and Finakis in the literature. Another notion that was proposed by Majumdar, Deshmukh, and associates is called Skorokhod distance, and I will simplify it a little bit for the purpose of explanation. Assume that you want to measure a proximity measure for these two continuous signals. You are doing that using an elastic rod that can expand and shrink, but it cannot expand beyond a certain length. That maximum length of the rod is called its length, basically. And the smallest rod that can keep these two signals in touch while moving over in time is called the Skorokhod distance of these two signals. So the elastic rod can tilt forward or backward, it can expand or shrink, but it cannot expand beyond its limit. And the smallest rod that can continuously keep these two signals in touch is called the Skorokhod distance of the two signals. Now these are two examples of conformance, and we wanted to formalize the notion of doping, and we said instead of defining a notion of doping that is specific to these notions of conformance, we actually define a generic notion of doping that could be instantiated by these two notions of conformance, and that we do using a theory of retiming. I won't go into the details are in the paper, but the idea is that we define classes of retiming functions that allow us to match a signal with another signal, and by specifying a class of retiming function we can recover a notion of conformance, including these two existing notions of conformance in the literature. So we have shown that both tau epsilon conformance and Skorokhod distance are examples of conformance using our retiming function with the specific types of retiming functions. So then we define a notion of doping that uses retiming functions to define when a system is on dope, and that's the next slide. So we say a system is clean when for all two valid conforming input trajectories with a given retiming function and a given bound on the difference in time and value, then for every response to the first input there is a response to the second input that is close enough to the first one, such that the outputs are also close enough with respect to their given proximity measure that we have defined for that particular domain. So we need to fix a proximity measure for inputs and a proximity measure for output and classes of retiming functions, and then you obtain a notion of doping. And we have instantiated that for tau epsilon conformance, and we have applied it to a case study that I'll present next. So for that, we rented a car, and we ran the new European driving cycle, which is a new standard to prevent doping on diesel emission. And we first devised a test cycle that is according to the standard. So the standard tells that you should run a certain amount of time, certain distance, using certain profiles, for example, an urban area, in motorways, etc. And we have designed a test cycle that is exactly according to the profile. And then we have also superimposed certain deviations on top of this test cycle. So, for example, we added a sine noise on top of that, and also we designed another deviation from the original input. You can read the details about this experiment in the paper, of which a short link is provided here. So we let those deviated signals, as well as the original ones, be driven by a human being, and because these are driven by a human being, you see slight differences also between the designed one and the actually driven test cycles. So the design test cycles are denoted here by the solid line, by the solid gray line, and the driven one are denoted by the dotted red lines. And interestingly, in some cases, we observed a threefold emission increase in those cycles that were extremely close to the original ones, and still allowed by the standard test cycles. So we could show that possibly there are issues with that vehicle, due to which it emits much more particles if we deviate a little bit from the test cycle that was originally designed. So the next step would be to automate this using machine learning techniques, and that's our ongoing research. So in conclusion, we have come out with a theory of approximate conformance using the notion of retiming that generalizes many notions of conformance in the literature. We have come up with a notion of doping detection that uses this generic notion of conformance, and this already generalizes many other existing notions of doping in the literature as well. Then we have applied this theory to the emission test using the new European driving cycle standard, and we have found some evidence that could indicate some type of doping, which requires further investigation. The roadmap is to build this into an automatic process where you can use machine learning to come up with models and then generate test cases from that model and iterate a few times until you have enough evidence for doping in such examples, and that's our ongoing and future research. That's all. Thank you very much for your attention, and I hope I can receive your questions during the online session at FORTE. Thank you, and bye.